Think Snell's law only applies to when you're looking at stuff that's underwater? Think again. My name's Alex, and this is the High Yield Science lesson on geometrical optics. After this lesson, you'll be able to explain the roles of the refractive properties of the different media of the eye, and you'll also be able to infer causes of myopia and hyperopia. Take a few seconds to read this short question stem. We're told here that cataracts might occasionally lead to alterations in the refractive index of the lens, which is our lead into the idea of Snell's law. We're also given a hint that this condition might lead to problems seen when the axial length of the eye is altered over time. What are the two problems associated with altered eye length? Myopia and hyperopia, which we'll explore in just a little bit. So just from this question stem, we were able to gather that the problem that's going to arise from changing the refractive index of the lens is probably going to be related to either hyperopia or myopia. With this prompt, we're really laying out the two ways in which the axial length of the eye can be varied. You can have an eye that's too short or an eye that's too long. Once we understand what happens with varied axial lengths, we'll be able to apply our findings when we look at what's happening with an eye that has a different refractive index of the lens. It might be tricky to try to consider why varied axial length might be a problem before looking at how a normal eye works. So let's do just that. Let's consider how rays are refracted in a normal eye, such as the one we see up top. With a normal eye, with a normal width, where is the image forming? It's supposed to form at the retina. So we see here we have an example of rays coming in and converging at the retina. But no matter how far apart the incoming rays are, they are always supposed to merge on the retina. That's what a normal eye works towards achieving, and that's what we see here with our second set of rays. Now looking at this eye, where does the last refraction of the light occur? In other words, at which point does the light travel in a straight line until it reaches the retina? As we can observe in the question stem, the vast majority of the eye is made of the vitreous humor, and there's nothing separating the vitreous humor from the retina. So the last refraction must be happening at the lens vitreous humor boundary. Once light is past that, it makes its way straight to the retina. What can we infer about the refractive apparatus of the eye if the only thing that's abnormal is the axial length? Since the whole converging system, let's call it the focal apparatus, is right in front of the eye, whether you have an eye that's too long or too short, that refractive apparatus is going to be normal. We indicate that on the eye that's above, but it's also applicable to our two abnormal eyes below. Okay, so we have a decent baseline understanding. Let's look at our abnormal eyes, starting with the one at the left that's too short. You have incoming rays of light. How differently will that eye refract the light compared to the eye above? It will refract light just the same, because the converging apparatus is normal, but because the eye is shorter than it should be and the rays converge the same, the image is actually going to be formed behind the retina, and that's a problem. And that problem is actually called hyperopia, or farsightedness, when you can see things from afar but not close. You can take a moment to consider why hyperopia is associated with farsightedness. In short, when objects are too close, the incoming rays are not parallel, right? That's an assumption we make when objects are very far, but rather they're diverging, and the eye has a difficult time converging them onto the retina. It's a tough concept, so I would definitely suggest drawing it out. In any case, clear vision happens when the image lands on the retina. If you had the power to change those rays to make for clear vision, what would you do to those rays? We said normal vision is when the image lands on the retina, so we'd want to bring those rays closer together. In other words, we'd want them to converge faster. And just like that, this means that the correcting lenses for hyperopia are actually going to be converging. Converging lenses are convex lenses. Those help the image form on the retina, as we see with the red rays. Now let's consider what's happening in myopia. The eye is too long and the focal apparatus is normal. Where is the image going to form? In front of the retina. So exactly the opposite of hyperopia, we want these rays to converge less than they actually do. We need diverging lenses, which are concave. Like we said earlier, we're likely going to have to use Snell's law to understand what happens when you change the refractive index of the lens. Honestly, you won't necessarily have to plug in values when you're dealing with Snell's law. A lot of times what can happen is that you'll just need to indicate whether the light will bend away, bend toward, or remain at the same angle compared to the normal. And being able to determine that requires you to know how increasing the angle alters its sign value. A good way to go about determining that is to pick up two pairs of angles and sign values. You should know 4 sign values. Let's use 2 for now. Sine of 90 degrees is 1, and sine of 45 is square root of 2 over 2. So it's pretty clear that when you go from 0 to 90 degrees, when the angle value increases, so does its respective sign value. Now for the two other sign values you should know. The sine of 30 degrees is 1/2, and the sine of 6 degrees is square root of 3 over 2. Do you notice the trend here? Sine of 0 is square root of 0 over 2, Sine of 30 is square root of 1 over 2. Sine of 45 is square root of 2 over 2. Sine of 60 is square root of 3 over 2. And sine of 90 is square root of 4 over 2. There's that square root of x over 4, where x goes from 0 to 4 for 5 angles. It's the exact same values for cosine, but in the opposite order. That's to say cosine of 0 is 1 and cosine of 90 is 0. We have everything we need at this point to understand what happens when the refractive index of the lens is altered. Specifically, we're told it's slightly increased with a greater density. We have a normal eye on the right, and we're zooming in on the lens. This eye has a normal axial length and a normal focal apparatus, which is why the image forms on the retina. Let's see what happens when we increase the refractive index of the lens. We have two incoming rays, but we'll focus on the top one just to avoid any confusion. The first thing we have to do is to consider what's happening at the aqueous humor lens interface, since that's the first place light is going to be refracted differently. Nothing's changed in the aqueous humor, and incoming rays are not changing either. If the refractive index of the lens is greater, how must the angle with which the light is refracted change? We have an equality here, so if the refractive index of the lens is increasing, the sine of the angle of the refracted ray must be smaller. Thanks to the relationship we just established, this means the angle will be smaller. So let's see what angle we're looking at. The normal line is seen here in gray, and in light green, we have the angle of interest. The ray will have to create an even smaller angle than what we see, which means that the top ray has to bend on more than it would in a normal eye. So now the ray is in the lens, and eventually it's going to have to make its way out into the vitreous humor. What component of the second line of equation must change in addition to the refractive index of the lens? It's once again the angle at which the light will be refracted coming out of the lens. If the refractive index of the lens is greater, how will that angle change? It will also be greater. In light purple, we have our second angle of interest, and we said it must be even greater. This means the top ray will have to bend down even more. We see that in this condition, the image is formed in front of the retina. What condition is this analogous to? This condition is analogous to myopia, and is in fact referred to as index myopia. So it's a type of myopia where the problem is not due to varied axial length of the eye, but rather to an altered refractive index of one of the medium of the eye. In this case, it was the lens. Together, we've looked at the role of the refractive properties of the different ocular media, but we've also seen how alterations to these properties might lead to myopia or hyperopia. So really what we did in this lesson is that we've integrated different concepts such as Snell's law and lenses, but make sure to study those independently so that you can make sense of how they fit together. See you next time.